I'm here to introduce Avikar Periwal. Avikar is a postdoc in the Doyle Group at Harvard, where he works on laser-cooled molecule systems. He completed his PhD just recently from Stanford, and then now he's getting started at Harvard. He's going to tell us about some of the work he's doing there. So please welcome Avikar.
Thanks, everyone. Thanks for having me. Today, I'm going to tell you a little bit about laser cooling molecules and specifically sort of for quantum science, and a little bit how working with the molecules kind of teaches us maybe some new things that can be used with atoms and sort of simpler systems as well. But sort of big picture, I guess maybe this is in kind of every quantum control talk. There's a variety of motivations for why we want to build sort of systems of controlled quantum particles. So one is quantum simulation. That we can make maybe some sort of toy model in the lab and probe it in a very controlled way, and then go back and kind of match what we see experimentally to various models or sort of computational methods. Right? Another sort of application is enhanced sensing. So atoms and molecules are some of the most precise sensors of time for clocks, or even for measurements of violations of fundamental symmetries. And so sort of the more control and the more even just number of particles you can control, kind of the better your measurements can be, and kind of the more precise, more stringent limits you can place on some models and sort of some probes of new physics. And finally, I guess from a more engineering perspective, these are all the toolkit, that you need for quantum computation, which maybe has some possibility for solving new problems, even if it's just factoring numbers. Okay, but there's sort of two axes, I'd say, in quantum control that are a little bit diametrically opposed. So one is the number of particles you have control over, and the other is sort of the amount of control you have over these particles. And so when we're looking for new physics, basically the goal is always to push kind of your radius in this space. Right? And depending on the task you're looking at doing, there's maybe you want to push kind of in different axes. So if you want to do high precision measurements, maybe your fundamental limit is actually just statistical noise, and you want to have as many particles as you can under control. Whereas for sort of simulation, maybe you want really access to every possible degree of freedom, but you don't need more than 20 particles to reach a regime where you can't classically compute things anymore. And so depending on what you want to do, there's kind of a variety of different platforms that people take experimentally, right? So one very common platform, or let's say popular in industry, is kind of this idea of using superconducting resonators as qubits. This is the approach that's taken at sort of Google and Amazon a little bit, but also in academic contexts. And these kind of devices can be used also for probes of dark matter, for example. Another sort of common setting is to use ions. So what I mean by that is some sort of charged atom, and this charge makes them kind of easier to manage in electromagnetic traps. And these form a basis for some of the world's best clocks, and also they have kind of a very long history over the past 30 years of developing kind of a toolkit for quantum computation. And now if you just sort of add an electron back to the ion, then you have neutral atoms, which have seen really, I'd say, like a remarkable growth over the last 20 years. So I'm going to talk about this kind of avenue for quantum control, but not really atoms, just neutral particles, like molecules in particular. And so the reason that these kind of neutral particles are really nice from a quantum setting is basically a couple of things. So one is it's easy to scale. So an atom or a molecule you can trap in a single laser beam, right? And so as long as I have basically a linearly increasing amount of laser power, I can trap, a linearly growing number of particles. And if I'm thinking about this in a quantum mechanical perspective, that means a linear scaling in money and laser power gives me kind of an exponential scaling in Hilbert space. Okay. And the other really nice thing is that there's been a lot of techniques developed for imaging. Right. So this picture from Penn State shows individual atoms image in a three-dimensional lattice in different pancakes. Right. So these neutral particles are easily controlled basically entirely with optical manipulation. But the tricky thing from a quantum control perspective is how do you make neutral particles interact? Yeah.
So quick question. So for the scalability picture or this PSU picture, do you need one laser spot per atom, or do you just modulate the laser in such a way that you can move an individual atom?
Yeah. So people do different things. So this particular picture is an averaged image of 10,000 atoms. There, they send a single beam onto a device called a spatial light modulator, and that generates a pattern of 10,000 spots, and they trap an atom in each one of those individual spots. The picture on your right is made in a lattice. So what you do there is take two beams and or a single beam and retroflect. So you have two counter-propagating beams. That forms a standing wave, and you can trap inside at the node or antinode of that standing wave, and an individual atom. And so if you do that in 3 dimensions, you can have a 3-dimensional lattice. Yeah. So if you want to access this kind of large Hilbert space, you need to generate entanglement in some way. You need some way for information to spread between these, quantum particles. And so, as their name sort of suggests, it's not necessarily trivial to do this with neutral particles. So for atoms, these interactions that generate entanglement, there's kind of a few different approaches that people take. One is to put them in these sort of optical lattices, and now atoms can actually just hop between different lattice sites and interact with other atoms. And as you can take pictures, you can kind of see the dynamics or the states that are generated in this kind of situation. The other approach is to use the atomic structure and excite to high-lying states. So these are so-called Rydberg states. And the idea here is that you can excite the electron of the atom to a state where its effective radius is on the order of the spacing between particles. So now, since the electron carries some spin information, you can basically use that to transmit quantum information between particles. And this has been sort of the sort of Rydberg platform in general is really, I think, a hotbed for quantum computing development, because it has some nice properties in terms of, let's say, rejection of experimental noise, especially in sort of motion of that. Okay. But these kind of different approaches are useful for different things. So these lattice experiments map very directly to a lot of condensed matter questions. Right? So this basically allows you to try to visualize the microscopics of what you think are happening in some sort of 2D material potentially, in like a very direct way, where you have an analogy basically mapping your atom to an electron in a solid. And I'd say in the last few years, we've seen this kind of moving from a regime where this is the promise of the optical lattice experiments to it's starting to be used, I think, in a way that is potentially helpful. So this particular example, there are kind of these two different sets of papers looking at this Nagaoka effect, which was sort of described in the 60s. And so there's a a demonstration on the right in a bulk material, and kind of at the same time, two groups used fermionic atoms in an optical lattice to kind of try to probe this in kind of systems of sort of 100 atoms, and look at kind of microscopic correlations. For neutral atoms with Rydberg interactions, there are sort of quantum computing platforms that are being used, and because atoms can be used for some of the best clocks in the world, these kind of entanglement generation methods are now starting to be used to make quantum enhanced clocks. So these are all ways that atoms have been used really to probe various quantum effects. So the question I think really is like, well, why would you want to use molecules? And the answer is basically, well, there's more stuff going on, and so there's more things you can control, and maybe there's unique things that you can try to leverage. And so the two things really are that there are more internal levels in a molecule than in an atom, and sort of more geometric structure. These are kind of sort of the same thing. What I mean by that is in molecules in particular, I have vibrational energy levels and kind of rotational energy levels, whereas an atom is really sort of just a point source, right? So these are uniquely molecular energy structures. And then if I have a polar molecule, for example, I now have a permanent electric dipole moment, right? So if I work on calcium monofluoride, there's a calcium atom, which has basically an extra electron, and a fluorine atom, which kind of wants to pull an electron. So you can have an electron that is primarily around the fluorine that gives me a permanent electric dipole moment, even if I'm just sitting in my ground state. And just to keep kind of some experimental numbers in mind, these vibrational levels are typically spaced by terahertz frequencies. That's not something you're going to commonly find sources for, but it's basically the peak of the black body spectrum at room temperature. And these rotational levels are kind of on the tens of gigahertz. So it's sort of Wi-Fi frequencies or cell phone frequencies. Okay.
Sorry, you said calcium monofluoride?
Yes.
How do you get calcium monofluoride?
We're going to talk about that soon. Yeah. We'll get to it. Okay. And so this permanent electric dipole moment allows you to have dipole-dipole interactions without doing any excitation, just sort of sitting there naturally. So it becomes kind of a nice setting for some spin models and some quantum simulations. The other thing I'd say is if you can control molecules, this gives you really a nice window into ultra-cold chemistry, right? Instead of simulating something, you can just actually prepare two molecules in particular states, bring them together, and see what the reaction rate is. And then the other reason is kind of precision measurement, which I sort of mentioned a little earlier, but the large sort of internal electric fields actually make polar molecules extremely sensitive as probes for violations of fundamental symmetries. And the kind of state-of-the-art levels of these experiments you can find in there's the Acme collaboration at Northwestern, and there's an ion experiment at Gila in Colorado. These kind of experiments are set limits that are sort of, depending on your model, kind of further at higher effective energy scales than the LHC at the time. Now, these kind of terahertz vibrational levels give you access to different clocks. And there are various forms of various vibrational levels that can have some sensitivity to kind of proton to electron mass ratios. And I think there's promise in doing spectroscopy that'll maybe do, that can do kind of state-of-the-art measurements of some of these kind of fundamental constants. Okay. But today we're going to talk about, how do you make a cold molecule, and then kind of some new mechanisms that we saw in how you can trap and cool these molecules. And then I'll talk a little bit about some ideas we're working on to try to harness these dipole-dipole interactions. Okay. So controlling molecules because of these levels is very hard, right? So in an atomic system, what you rely on is the fact that you have these closed electrical transitions. So I can send a laser at an atom, it'll excite and fall back to some level. And basically, I can keep doing this over and over and over, like infinitely many times effectively. And so this is the sort of fundamental mechanism that people use to remove entropy, remove energy from atomic motion. And that's how people will trap these sort of single individual atoms, cool them to whatever motional ground state, make Bose-Einstein condensates, all these things. Now, vibrational transitions are sort of fundamentally not closed, right? So this is basically a foundational reason as to why using this kind of control is very hard. So if you want to have a cold molecule, really there's not a lot of ways to do this if you just think of it only as an atom. So there's kind of two approaches that people take experimentally. The first is, well, a molecule is at least two atoms, but we can control two atoms and bring them together and associate them, and that's a molecule. So that's the idea with they're associated molecular experiments. You can use basically Feshbach resonances to bring two controlled atoms together and turn them into a molecule where it's motional, electric, vibrational rotational state. And this is a very, very active area of research. Just in the last year, people were able to use this to make the first Bose-Einstein condensates of sodium cesium associated molecules. Okay. The other approach is you can just say, well, I'm going to try to address as many levels as I can with lasers. And that's what I'm going to talk about today. And so the approach we use is basically exemplified by this calcium fluoride molecule. And so the idea here is, you have this electron and this strong bond. And if you look actually at the kind of first few electric excited states of the molecule, it looks pretty similar to like an atomic electron orbital. So this is, if you don't look super closely, it's sort of an s orbital and sort of a p orbital and s. And as I said, vibrational transitions are not closed. But if you look at the decays in calcium fluoride to the first vibrational state, 98% of the time you come back to the ground vibrational state in this first excited state. 2% of the time you go to the first, right? And if you go out, that's sort of a, 1 in every 100,000 photons is exciting you, is decaying into this third excited state, right? And actually, if you look at kind of the second state, this B state, these ratios get even better. So they're almost closed, right? And so these are, you want basically these diagonal Frank-Condon factors so that you can cycle as many photons as possible, right? And so this was kind of pointed out in the early 2000s by De Rosa. And the question then is basically, well, is almost closed actually good enough to do something, right? Because we have these decays, eventually you'll decay into some dark vibrational state, which you aren't addressing, and now you've lost your molecule. You can't do anything with it. All right. So just to hammer this home, people have used direct laser cooling with CaOH, right? So CAF, your vibrations are this. With CaOH, you have like this vibration, you have this vibration, you have like vibrations in and out of the plane. So they need, about 12 lasers, and they can cycle, uh, 30,000 photons, really. With calcium fluoride, we can cycle about 200,000 photons with just these sort of 3 rebumping lasers for the first few vibrational levels. Okay, but because you have a finite photon number, that means you have to start cold. The other reason you have to start cold is because at room temperature, so this vibrational energy level is kind of the peak of your black body spectrum. That means you're split out actually over a number of vibrational levels, and each one of those is going to have a ton of rotational levels covered, right? So if I want to start out in a place where I can address and be in a sort of small setting, you have to start with a cold sample. So the way we do this is by taking a chunk of calcium metal and ablating with just a sort of Nd:YAG, like a not super strong pulse laser. And this is happening inside a box that is kept at somewhere between 2 and 4 Kelvin. And then we flow in SF6 gas. So when you send in this ablation laser, you're generating basically a cloud of extremely hot, excited calcium molecules, or atoms and ions, and they'll react with the SF6 gas and form a bunch of stuff. And one of the things they form is just CAF radicals, right? Because CAF is, you can't just buy it at the store. And so now you have basically hot CAF gas, and the meat of all the cooling happens because we flow in an inert buffer gas, just helium in this case, sort of depends on what temperature you're trying to reach. And that causes a bunch of just elastic collisions, and now you have 2 Kelvin CAF that then exits this cell. And so you have a beam moving at like 100 meters per second, but this is now basically at the regime where you can start to use this finite number of photons to get down to very low temperature.
Right. All right. So back to my question about CAF. I thought CAF is +2, right?
So calcium is like has 2.
Right. So I would have thought it would be CAF2 and not CAF.
Yeah. So CAF2 you can buy in crystals. Right.
So
but you can have a CAF, like a neutral CAF. It just is very polar and reactive. So you can't like get it in a test tube.
Sure.
But if it's in a vacuum chamber, then there's nothing to react with.
Right. And you're saying that that's just in the setup that you have in the vacuum CAF is just stable. It's stable enough to last.
Yeah. So it's like it's just CAF molecules. Or so I would say in here, there's a bunch of other stuff. And at some point you start to become limited by basically chemistry and collisions with other things. Mm-hmm. But for the numbers that we're using, it's not the limitation yet. Yeah.
But so when you do this, like how much CAF do you get versus like wouldn't CAF2 form like preferentially?
So I think this actual like ablation and production, I would say my sense is don't have like a super good understanding of the dynamics, especially because this is happening in like a cold box. So you have all these issues where, SF6 might be like frozen on the surface. So I think the actual like set of productions we don't understand super well. But I'd say like you basically produce enough CAF that because your lasers are only addressing CAF, it's enough to do the next set of steps. But I also think this ablation process is extremely violent, and so I think some of the like room temperature intuition doesn't quite hold in that.
And I guess maybe this is the next slide. You'll tell us how you separate out the CAF from all the other.
Oh, so it's basically just the laser only is resonant with CAF transitions. So
and the gas is dilute enough so that the laser's not, being by other stuff.
So this is all happening in a vacuum chamber, which we're pumping down, and so like maybe like every few months we have to open everything up, and there's like lots of dust on things. that we have to clean up, and that kind of stuff. But yeah, the other thing is like, helium at these temperatures, you have to be like somewhat wary of. So, and actually, I guess everything you have to be wary of. So around this box and sort of on different radiation shield, we'll have charcoal plates, which will absorb a lot of the helium and a lot of the other products. Yeah. Okay. So this kind of production mechanism is called cryogenic buffer gas cooling, right? And this is really the meat of what we're doing, is we're going from basically thousands of Kelvin of energy down to 2 in this kind of person. And so if you sort of calculate out the expected energy, this cools you down to a few rovibrational states, right? And in fact, like almost entirely you're in the first vibrational state, and you're just populating some of the lowest rotational states of that vibrational. And this box is called a cryogenic buffer gas box, so CBGB, which is named after this punk rock club from in New York. Look it up. I guess it's a little older than me, but maybe not much. Okay. But yeah, so once you have this beam, you can start to use the sort of transitions that I showed you, this level diagram. You can now sort of laser slow, and kind of all the techniques that people have developed for atoms, I would say to a large degree, just work. But they just work a little worse because you have to be careful because you have a finite number of photons you're working with. But you can trap in a magneto-optical trap. I think at this point you can sort of routinely trap maybe 100,000 calcium fluoride molecules in a magneto-optical trap. So these are now at millikelvin temperatures, and all the atomic sort of sub-Doppler cooling techniques also just work. And so you can cool in free space down to these sort of micro Kelvin temperatures. Once you have this cooling, you can load into a sort of conservative trap or load single molecules into tweezers. And this technique is used basically for all of these molecular species that are being used for direct laser. And so I showed some here and sort of roughly where they are in terms of overall, in terms of where on this pipeline they can be used, and different molecules are kind of used for different purposes. So like aluminum fluoride, for example, looks very similar as a molecule to some of the atoms that people use for clocks. So it has some very narrow transitions that people like to use. Same with YO, SROH, and YBOH have very good sensitivity to kind of probes of physics beyond the standard model. Okay. So that's roughly how we make the molecules, and maybe I'll just say a little about what's been done with them. So in tweezers, these are images of individual molecules trapped in optical tweezers. And this has been used to, for example, look at controlled collisions between molecules. And it turns out you can apply microwave radiation. So just some 20 gigahertz source. And if you apply it at a precise frequency and polarization, you can actually suppress collisions and suppress the rate of reactions of two molecules, right? So if I have individually controlled molecules and bring them together, I can just directly measure the collisional rate by looking at loss, and you can suppress that by sort of changing your reaction pathway appropriately. And so this is kind of an observation of what's called microwave shielding, and this is kind of the fundamental technique that was needed to go back to these Feshbach molecules. what they got really good at was doing this microwave shielding to suppress kind of lossy collisions, and then they can do evaporative cooling down to generous. The rotational levels in calcium fluoride give you actually a very nice set of qubit states. So if you look at the ground rotational level in a CF molecule, there's 4 levels that it splits into, from some hyperfine interaction when you apply it. And when you apply a magnetic field, then you have like a Zeeman effect. The first excited state splits into 12 levels. So this kind of complexity is maybe like irritating in some contexts, right? Like it's more complicated than an atom. But because you have so many different levels, you have sort of more choices for which pairs of levels you choose for a qubit. So if you choose these particular 2 levels, they happen to have good properties for maintaining coherence with respect to kind of usual experimental imperfections like magnetic field noise or the actual trapping light. But you can also choose levels that happen to be like almost completely insensitive to magnetic field noise, but more sensitive to trapping light, or sort of vice versa. So in general, you can kind of find appropriate polarization and trapping conditions to extend sort of a coherence time, an effective coherence time, out to, this is a measurement from like 2019, so it showed out to like 600 milliseconds or so. Now we're out to like maybe 1.5 or 2 seconds in calcium fluoride, and people have demonstrated in other species coherence times of more than 10 seconds. Now these qubit states, you can start to leverage this internal electric dipole moment to look at sort of entanglement generation. So in a few years ago, they kind of upgraded to tighter focus tweezers and can look at sort of coherent pairs, oscillations of pairs of molecules. So these kind of oscillations tell you that a pair of molecules is like oscillating kind of the same way. They have then this correlation you can use to kind of probe directly how your entanglement, or you can generate entanglement between 2 molecules by sort of starting with a product state and allowing yourself to evolve for a certain amount of time. You can probe by looking at basically how correlated are the 2 individual molecular states, and you can see a sort of effective Bell state fidelity of around 90%. So for comparison, for a quantum computer, for a fault-tolerant quantum computer, you probably want something like 99.9% to sort of hit a threshold. But this is a few years ago. There's been developments in other molecular platforms, so it's now at sort of 98%. And so one nice thing about molecules is if you combine these 2 numbers roughly, like the interaction strength, which is on the order of kilohertz, and the coherence time, which is on the order of seconds, nominally you're looking at kind of thousands or tens of thousands of sort of coherent oscillation cycles. And there's no kind of fundamental decay on this time scale. So if I excite to a Rydberg atom, I always have to worry about decay from my Rydberg state. But here there's not like a fundamental decay mechanism in some sense. So the promise is that you have some platform for very deep, coherent many-body physics.
Sorry, can you clarify? You say second scales coherence, but all the graphs are on milliseconds.
Oh yeah, so this is, I just wanted to be consistent with using CAF. So this particular measurement shows like a half-second scale coherence time. Yeah, experimentally, like in our current apparatus, it's like a factor of 3 to 4 more. In some species, like there's a rubidium cesium associated experiment where there's a nice magic wavelength that's more than 10 seconds. And then, yeah, these are kind of kilohertz scale interactions. And in like sodium CP, for example, a larger dipole moment, kilohertz scale bell pair. So it's sort of, I wouldn't say this, like this part is not experimentally demonstrated. This is more of like the promise, I would say. Okay, and then let me just say that the kind of atomic toolkit can be used really to cool down your molecule extremely well. So we both demonstrated Raman sideband cooling. So now you have actually a molecule and it's in a trap in its motional ground state, electronic, vibrational, rotational, like full quantum controls over individual molecule. Now the limitations in general for this platform are there's relatively low loading efficiency into the tweezers. There's not great, it limits your statistics, your ability to kind of do more. And these are all kind of one-dimensional systems. But if you can't load well, then it doesn't make sense to push into higher dimensional systems. Okay. So sort of motivated by this like lack of, molecules, this led to kind of a development of this conveyor belt mod, which we'll talk about. So in particular, it's kind of in between the loading into a conservative trap and the magneto-optical trap. So sort of prior to this work, the number in the dipole trap was for roughly 1,000. If you're coming from about 100,000 molecules in your magneto-optical trap. And the reason for that is actually a little subtle. So the key point when we do these manipulations is if we're looking for a closed transition, right? And that relies on what we call selection rules, which is just how is angular momentum conserved when your light interacts with your molecule or atom. Okay, so the electronic levels of the molecule are going to behave as atoms do. There's no difference. But these split into vibrational levels. We've talked about how there are no selection rules here. And these then split into vibrational levels, right? Now the sort of vibrational selection rule, we're going to quantize these levels by n, is that delta n is plus minus 1. What that means is if I start from n equals 0, I excite to n equals 1. I can decay now into n equals 2 or into n equals 0, right? So this is going to leave me with some dark state, or I'm going to have to repump my n equals 2 transition. So what you can do instead of having dark states is if I drive from n equals 1 to n equals 0, right? Then the 0 state, if it's going to decay in a plus minus 1 way, has to decay back to 1. Right? So this gives me this kind of closed cycle. Okay. But that means that, because every molecule has these rotational levels, your molecular mott must use this kind of what's called type 2 transition. The excited state angular momentum is smaller than the ground state angular momentum. And so you can look at kind of, if you send in your mott light or your trapping light, what is the kind of force as a function of velocity look like? Right? And so depending on whether you send in red detuned light or blue detuned light, that'll give you this red curve or blue curve. But the key point here is that for large velocities with red detuned light, I have a force that is in the opposite direction of my velocity. So that's gonna, slow me down. Whereas for the blue detuned light, I'm gonna have a force that is in the direction of my velocity, right? So that's gonna accelerate me away. right? But if you look at actually the low velocity class, it's the opposite effect, right? Now, that means that I have with red detuned light cooling light, but what's called sub-Doppler heating. So at the Doppler limit, I now have heating effects. With blue detuned light, I have heating, but actually sub-Doppler cooling, but it doesn't matter if I'm just trying to cool down, right? And what this means is, for atoms, you can use type 1 transition, you can have cooling and sub-Doppler cooling, right? But with a molecule, you're going to have this sub-Doppler heating. That's going to mean that your MOT is actually quite hot and diffuse. So this is a picture of a dipole trap, or conservative trap, overlaid with the MOT. And so the limitation on loading is basically entirely a mode mismatch issue, where you can't actually your molecule's just not seeing the trap. Okay. But what you can do then is say, well, what if I try to harness the sub-Doppler cooling part of this, right? And so after loading my red detuned MOT, I then switch, once it's sort of equilibrated around this region, to a blue MOT. And so people have done this in a variety of species. So this is YO from Boulder, calcium fluoride in Princeton, and strontium fluoride at Chicago. And so this clearly works, and you can see that the main thing you get is this diffuse cloud gets compressed, right? So it kind of will help. But there was additionally, so they tried to do this at Harvard in actually the CAOH experiment. And they noticed something kind of weird. So in CAOH, the levels here are split by a very small amount compared to kind of the natural alignment of their excited state. Of their sort of main transition. And they found that if they shined two frequencies of light, they were trying to kind of use a 2-photon transition, but they found that if they shine these two frequencies of light, they got much better compression than with the kind of standard blue MOT, orders of magnitude. And I think this wasn't immediately understood what exactly was going on. And so, the nice thing about having these experiments so close to each other is, well, you can just try the same thing in CAF. And you saw also kind of the same effect with this 3-frequency MOT. And in particular, there's this an order of magnitude reduction in radius, gives you almost factor of 1,000 increase in density, with reasonable transfer efficiency from the red MOT into the blue MOT. And because you have the sub-Doppler cooling, you're going from kind of millikelvin to 100 microkelvin. Okay, so now I'm going to say this is on par with atomic MOTs. Realistically, it's on par with a not so good atomic MOT, but ballpark. But this kind of led to sort of, I'd say, more understanding of the physics that's going on. So in particular, CAF, all these energy scales are of the kind of sub-levels in this particular rotational level are well resolved. But you still saw this kind of improvement with having a second blue-detuned beam with a different polarization. And so the key idea here is that in the optical trap, you're sending counter-propagating beams. And if you use different polarizations, then I have actually two pairs of beams I should think about. Okay. So this purple beam, when it retroreflects, has now, if it's sigma minus going one way, it'll flip its polarization, so sigma plus coming the other way. And so it's not, directly interfering, or it is interfering, but it's moving. It's not a standing wave. if I send in a sigma plus beam now, which is this green light, that will have the same polarization and will interfere, right? So if I send in these two polarizations, what I'm actually getting is two sets of lattices. But if they have a different frequency, then the lattice is going to be moving. If it's the same frequency, it's a standing wave. If the frequency is changing, then the effective lattice is moving at some velocity. So you have these two moving lattices, right? And these are the conveyor belts. And so if you can have your molecule load into the correct conveyor belt, depending on its position, you can actually sort of move the molecule towards the center of your mod. That's the idea, right? And so the question then is, how do you select the correct moving lattice, right? Because if you end up with the wrong one, you're actually moving away from the center. And actually the point is that the other part of a magneto-optical trap is you have a magnetic field gradient, which adds position confinement, and that gives you sort of natural selection of specific magnetic sublevels into the right lattice, because you're biasing the energy of, magnetic sublevels on one side and the other side. Okay, so the idea here is really that molecules that are further away get moved into a lattice that moves them towards the center while simultaneously moving them. And you can see this in actually just a Monte Carlo simulation of different molecules. So we're going to start off with the position distribution of molecules on the left and the velocity distribution on the right. And so you can see as you turn this on, there are two peaks that form in the velocity class. And those are the two conveyor belts that move towards the center. And you end up with this pile up then of zero velocity molecules at the center. And so this kind of conveyor belt mechanism, was like, I think, very not expected, really, but is actually, we think, fairly broadly applicable. Should work also in sort of atomic traps where you want higher density as well. Okay, just to give a sense of numbers, this kind of minimal size happens when the conveyor belt moves at like half a meter per second. So it's sort of very leisurely stroll. And then you can see, because we can make the trap now sort of 60 microns in diameter, the loading efficiency can go, almost an order of magnitude higher. And we think this is actually limited just by our laser power and the fact that the trap is reasonably small. Okay, so this leads to now 20,000 molecules loaded in a trap, and we think basically we're not yet limited by collisions between molecules, but maybe soon. Okay, so this is now an order of magnitude in the number of molecules in the trap, and just with the last little bit of time, I'm going to talk a bit about our ideas of using dynamics in the optical tweezers. So recently we kind of did another upgrade, and we have now 2D arrays of molecules. Have to make these implementary images. But if you look at these kind of measurements, you'd see that it actually looks like the oscillations that I talked about just wash away. And in particular, you notice as you move closer together or at faster speeds, you wash out more. And this is limited, we think, in a large degree by thermal motion. So as molecules move in the trap, their interaction strength is going to change. And then you average out over those different interaction strengths, and that leads to overall decoherence. All right. And you can see this actually, the tweezer is anisotropic. So the interaction strength depends on the angle at which you place your tweezers. As you vary the angle, if you look, for example, at 90 degrees, you have a factor of 2 smaller interaction than if you have 0 degrees. But you'll notice that 90 in red is looks a little more coherent than 0 degrees in blue. And so it's basically the orientation of your molecular wave packet determines or affects your interaction coherence. And you can just look at what's the distribution of interaction strengths I get as a function of this angle. And you can see that there is a point where, we're sort of broadest here at 0 angle and narrower at this 90-degree angle. But the kind of optimal place where you're most narrow happens sort of, it wasn't intuitive to me initially, I would say, at a place with non-zero interaction strength, right? So there's sort of, we think, a magic angle where you should see more coherent interactions. That's the hope. And if you zoom into this angle, which is roughly 60 degrees, the sort of effective quality factor you should expect to see improves with lower temperature. So this NZ is the motional quantum number, or average motional quantum number of the molecule in the trap. And we see sort of very preliminary evidence of this kind of magic angle with hot molecules. This kind of large like improvement in coherence at 0 angle is because of 200 nanometer like focus offset between the traps we used for the interaction. And so we're working basically on improving our cooling to try to see this effect a little more. But the other thing we've been thinking about is that these interactions happen on a kilohertz timescale. In our kind of Rydberg platform, these interactions or gates are happening on kind of hundreds of nanoseconds. So these interactions are quite slow. And we want to say, well, is this a good or like a bug or a feature? I would say generically it's probably not ideal. But the slow interactions give you now some possibility of using classical control techniques simultaneous or like during your kind of entangling operations, right? So people have developed these Rydberg platforms where they do digital approaches and move in between gates. The molecules, you now have this ability to move like concurrent to doing your gates or any kind of coherent evolution. Okay, so one example is this kind of magic angle now limits you to interactions in only one dimension, right? So if you want to, look at two-dimensional systems, you necessarily would have some decoherence, and we came up with a sort of protocol to cancel motion in 2 dimensions. So if you have a square lattice, let's say, you can select half your trap and move them contiguously in such a way that you basically average over all the thermal motion, and you should be able to see sort of the same non-zero interaction while suppressing any kind of thermally induced dephasing. And the last thing I'll just say is we've thought a little bit about applications in this precision measurement aspect. So one thing, one application of entanglement is for squeezing. And this is basically just a protocol for harnessing, your entanglement for enhanced metrology. And the idea is pretty simple. If I have a Heisenberg uncertainty principle, I would say I have 2 observables that I can't measure simultaneously, and the product of their uncertainties is bounded, right? And this is, this standard quantum limit. So normally what we think of is if we have sort of n sensors, we have an uncertainty that's like square root the number of sensors, and we think of it as being like uniform over these 2 observables, right? Position and momentum, for example. Now, if these sensors are entangled, you can actually reshape this ellipse. So you can't beat Heisenberg, but you can have a specific observable, right? Like maybe you want to measure just position, or just momentum, you can measure that extremely or more precisely, right? The scaling proves the 1/n. So this is used actually in LIGO kind of all the time with squeezed states of light, and I think that's improved their kind of detection rate pretty dramatically. But it's also been shown in a variety of different atomic species. And the idea here is actually you want really symmetric entanglement between all your different sensors. And this ability to rearrange your molecules or move your molecules while you're entangling them allows you to actually like directly sort of symmetrize all the interactions and therefore symmetrize the kind of generated entangled states. So in particular, we think we have some protocols for generating these squeeze states that kind of approach the all-to-all limit in terms of the measurement enhancement you could get, and it's sort of strictly better than what you can do with just sort of static arrays of molecules. And there's sort of a variety of protocols that work. And yeah, so we're in the process of starting to look at these different protocols, and sort of just built up the experimental apparatus and robustness needed to start looking at many bodies. And with that, let me just thank the Doyle group. So it's the whole group, and then Scarlett, Dachi, and Shinshu are the students on the experiment. But yeah, thank you.
So I have a question about, like, I guess the CAF system and kind of all these other small molecular systems. So you were mentioning how, like, you want this closed loop idea. Is it like, so with all of these small molecules, CAF, YBOH, or anything, was it kind of a matter of luck that the surfaces between these two states were just off vertical enough that it's like, okay, well, we get these ratios that you want? Or was there kind of like a theoretical basis already that said, oh, these will make good systems?
Yeah, so this no selection rules
Yeah.
is true. Basically, what you actually want is okay. There's some like binding potential, right? So if I have two atoms very far away, you can think of it as like an unbound molecule. And as I bring them closer together, it's some different amount of excitation, vibrational excitation. And if you excite to like, your excited electronic state, that potential is different. So ideally, what you're looking for is that the ground state potential and the excited state potential look as similar as possible. Right? So that's actually why like this ground state and the B state, so the second excited state, they have a more similar looking potential, right? They're like this sort of sigma S type kind of orbital, and so that they end up looking more similar, which gives you better Frank Condon factors. But there's a whole class that work pretty well, and I'd say in general, actually, just this whole idea of taking like a group 2, like calcium, strontium, whatever, and attaching something reactive. So that's why there's also CaOH, or like CaOCH3, for example, is also like you're basically laser cooling a calcium ion, and there's some stuff stuck to it that's kind of sympathetic. Yeah.
So I have a kind of more abstract question. So you mentioned at some point that there's attempts at going beyond standard model physics in these systems. So of course, most physicists are just trying to go to high energies to get at that. I'm vaguely aware of some propositions to do that in like the AMO space, but I haven't really gotten to the weeds. I was wondering, could you talk more about that?
Sure. Yeah. So basically, I think the kind of the nicest example are really these moment searches. So or like violations of fundamental symmetries. So the sort of canonical thing you look for, or one thing you can look for, is like a CP violating moment, right? So that would be like an electric dipole moment on a fundamental charge. Because it's sort of its mirror image would now be not the same, right? So there's searches for the electron electric dipole moment, and you'd say that in particular that the Hamiltonian for that interaction is going to look like the dipole moment, the electron electric dipole moment, times some applied electric field. And so polar molecules have an extremely large internal electric field, right? Which means that if you can, you'll see the effect on the electron, right, from that internal field. So it's like 100 gigavolts per centimeter or something. It's like well beyond anything anyone can do in the lab, and it's extremely well controlled because you're in specific states. So this gives you like, you can do some measurement, and no one's found this moment yet. So you can put a bound on it though, right? And you'd say like based on the standard model, we expect some limit, right? Based on any extension of the standard model, we can also calculate what the limit would be. And that's almost always like larger because you're looking, these kind of symmetry violations are also necessary to explain like matter antimatter asymmetry, right?
I see. So unlike, as I understand it, the high energy crew, which is kind of on the particle detection space, this is more in like symmetry analysis at low energy. Is kind of what low temperature, like you're not smashing things into each other really fast, right? So the interactions are very strong within the molecule, but this seems like this is a very different approach than most of what I hear in this department about like beyond standard model. I was just curious. Okay,
yeah,
that makes sense.
Yeah, I guess maybe basically you can say like up to some factor, basically like this theory is ruled out, and you can map it to like an effective energy scale at the LHC or whatever you could call it.
Okay.
For the ablation step, like when you're creating these CF molecules, in the moment, what is your feedback for knowing that you're generating enough? So do you put like a pressure sensor on the chamber and say, okay, well, we have enough particles in here, or are you going based on signal alone? I guess like how are you controlling the ablation laser to say, oh, our focus is good or our power is high enough to actually be getting what you want?
Yeah. So I guess basically a bunch of different metrics. So one is, we do have a pressure sensor, and you can see as you ablate, you get, some spike in pressure. If you have, for example, too much SF6 frozen on your target, then you'll see that the pressure spikes you get are a little lower. And, someone's just sitting there, monitoring, and you notice these things. You can see actually here, there's two windows. So you can send in, here or here or wherever, some light that is resonant with a CAF transition, and you can monitor absorption. That doesn't necessarily actually always directly correlate with your like final mod signal for, I think reasons people don't 100% understand like the dynamics in here, but I think it's like, you have as many sensors as you can, and if things look different from optimal, you kind of play around and figure it out.
I have another. What kind of intensities are like you dealing with at like the optical tweezer stage, like in these different dimensions? Like, so I'm assuming because you're retro-reflecting right back, that this is like some sort of like collimated beam. So how, like, what kind of laser power do you need to deal with to like get the effects that you want upon like this retroreflection, like at the interaction point?
Yeah. So for the actual tweezer, we don't want to retroreflect it. Or the reason being it'll form a well, there's a couple of reasons. So one is it'll form a standing wave,
Sure.
which will have like a weird shape. The other is it's actually like pretty hard to make a super nice, like as tight a spot as possible, right? So any retroreflection will add some aberration. So the actual tweezer, like the trapping light, we use 20 milliwatts per molecule initially. But which is like not a lot of absolute power, but you have to remember it's focused down to like about a micron square. So the intensity itself is fairly high. Yeah, so we right now are doing experiments with about like 30 to 40 tweezers, and for that we're using sort of a 5 watt 780 nanometer laser.
Well, if there are no more questions, let's thank the speaker one more time.